Hello, welcome to this introduction to smoldering wildfires. I'm Guillermo Rein. I'm a mechanical engineer here at Imperial College in London, and I've devoted some significant amount of my life into studying smoldering combustion. Before I did my PhD on the topic, I didn't know much about it. So I recognize that many of you might not know much about it. And there is a lot to miss because I hope I can convince you today that smoldering is an important phenomena for us to consider. The topic today will contain three main parts. I'm going to tell you what's smoldering, why it's important, and at the end I will discuss a little bit of what we know of how it ignites, how it spreads, and what it emits. The content of this lecture is mostly the work of my research group, and obviously with great contributions from other groups in the world, part of the literature. But in case you want to study more or read more without the Spanish accent, you can always go to these two chapters because I'm the author of the chapters. I made sure they're also in open access, so you can find them online just by having the title, and you don't have to worry about access to it. We'll start with explaining what smoldering combustion is. Smoldering is a type of combustion. Not all fires have a flame. This is flameless. It spreads slowly. The temperature is low, still burns, and will burn you definitely, but it's low temperature compared to a flame. And it typically happens when fuels are porous, when they are made of particles are put together or fibrous materials or material that has a lot of voids inside. The porosity of it plays a very important role, allowing oxygen to enter into the fuel, because the combustion process of smoldering is not a flame. So it's what we call heterogeneous combustion, because the oxygen in the air actually it oxidizes the fuel on the surface of the solid, not in the gas phase. That type of chemistry, which has this name, heterogeneous chemistry, it's a little bit of a ugly name. It imparts most of the characteristics of smoldering. It makes the amount of energy that is released to be significantly lower than a flame. It makes the temperature lower. It makes the spread lower, and it makes that the emissions, the smoke produced from smoldering, is very toxic. It has a very strong smell. Some people really like it because it means that the smoke contains a significant amount of hydrocarbons and complex chemical molecules that can actually, some of them, further burn and even release more energy or attack biological systems and life. Fuels that can smolder. There are many natural fuels that smolder, like wood, all types of biomass, peat, which we will discuss today, or litter, and even coal. There are also synthetic fuels that we humans have produced. We don't want them to be fuels, but they just became fuels, like cellulose, cellulosic materials, all natural fibers, and foams, like, for example, polyethylene foam that is used for insulation. There are many. Just some examples. This is a little bit of what we know. I'm going to show you a video that has been recorded in the lab, imaging as a thin layer of peat that is organic soil. We are seeing it from the top, and we ignite on one side. It has been accelerated 600 times, so I can actually show you this in just a minute. You can imagine the length of patience that the researchers need to have in the lab to study each of these experiments, and we conduct these experiments by the hundreds on any given year. The peak temperature at smoldering at the front, what is propagating, you can see here the infrared. This peak temperature over here is in the order of 600 Celsius for peat, maybe slightly higher for some fuels or slightly lower for others, but it's in the order of 600 Celsius, which is much lower than the peak temperature of a flame, which is in the order of 1,000 to 1,500 Celsius in a flame. The amount of heat that it releases is much smaller than the heat that a flame releases, about a third of the energy of a flame. And the spread rate is very slow. It's creeping, what we call creeping. It's about 1 millimeter per minute, whereas a flame propagates maybe a meter per minute. So significant, very significant types of significantly different types of combustion. This type of combustion then makes the fires, the smoldering fires and the flaming fires to have very different aspects. This is, I start with the flaming fire. This is flaming fire. You can see the flames with this yellowish, orange, red glow that I have. It typically burns the surface fuels, being the grass, the bushes, the underground, sorry, the overground, and even the trees. And they produce plumes, which have a significant amount of soot. It imparts this color to these plumes from gray, dark gray to even black. And this plume is very hot. So it actually, in the presence of gravity by buoyancy, it lifts up and can go into the atmosphere, sometimes very high into the atmosphere. So the plume is very buoyant. It's a surface phenomena. These flames move fast. We're talking about meters per minute. And the smoke is very sooty. Whereas this is a smoldering over here. This is a very different phenomena. First is that the plume that it produces is not as hot as the flaming plume. So it's not as buoyant. So it doesn't go high up. It actually stays after a few meters, no more than the height of a building. And it starts to propagate laterally. It actually floods the land and it doesn't go high up. It actually stays in the region where it has been produced. And it leads to this phenomena that we call a haze. Just be mindful that my research group at Imperial College is called Hazelab, originally in reference to this haze that is produced by many peat fires. This smoke is a different color. It doesn't have as much soot. It's not black. It's more whitish or grayish. And it has a very complex mixture of chemicals inside, even nastier than the one on the flame. The fuel that has burned is not the surface fuel alone. It's actually the soil itself, the underground, and it actually has disappeared. And it burns and is converted into gases and ash. What is left is ash and a little bit of char, because char that might be ongoing burning, or char because some bits have extinguished that will not burn. When we look into the chemistry, this chemistry that we refer to as being heterogeneous, I'm going to tell you a little bit about the chemistry of the smoldering versus the chemistry of flaming. This will be the only chemistry that I discuss today. Both smoldering and flaming have a reaction in common. This is a reaction that we call pyrolysis. And is if you take wood or biomass or peat or branches and you heat them up, this biomass will actually produce a gas in the absence of a flame, just by heating it up. This gas, we call it pyrolysate, and it's a gas. And it will leave behind char, because all biomass chars. So the process of charring, the process of converting the solid into a char, leaves in the air this pyrolysate gas. And these two, the pyrolysate and the char, are actual fuels in the sense that they contain enough chemical energy that could be released in the form of heat. It's just a matter of which phenomena is going to extract that chemical energy, will lead to flaming or to smoldering. So in the case of a smoldering, what we have is the pyrolysis step that produces pyrolysate and char, and this char then oxidizes with the oxygen in the air to lead to an oxidation process, which is the core of combustion process. And then you will have CO2, typical product of combustion, and water and emissions, and it will leave behind ash, which is the mineral component of the fuel, of the biomass, that actually cannot burn and will be left always in the soil, or in the ground, or actually will fly away as small particles. Because the char is solid and the oxygen is gas, this mixture of phases, solid gas, is what leads to the heterogeneity, the heterogeneous process, because there are more than one phase. But we also have the ability in pyrolysis to burn the pyrolysate. So if you have pyrolysis, biomass pyrolysis, but this pyrolysate is a gas, and then this pyrolysate that is a gas burns with the oxygen in the gas, that will produce a flame. And this flame will release heat and will also produce carbon dioxide, water, and these sort of emissions. So you can see that the smoldering and flaming, they have both of them an oxidation process, but it's very different. One of them is burning the char, the other one is burning the pyrolysate, and the two of them have in common the pyrolysis reaction. Without pyrolysis, there would not be a smoldering nor flaming. but it's impossible not to have pyrolysis in biomass. When we look into the natural phenomena of smoldering, one thing that called the attention immediately of people studying wildfires is that it is the cause of very, very large fires. These are peatlands. Peat, so many of you will know even better than me, is a carbon sink, a natural carbon sink invented by nature, where it actually stores a former forest, a farmer's vegetation, in waterlogged conditions such that it doesn't degrade, it accumulates, it increases density, and it stays there for thousands of years. If they were to stay there for millions of years, thousands of millions of years, it would actually become coal. So coal is a very old peat, and peat is a very old dead forest or dead vegetation. So this soil that is rich in carbon, when actually is not meant to burn, it's meant to be in very high moisture conditions, supposed to be surrounded by water. If for whatever the reasons, natural, anthropogenic, accidental or incidental, if it's dry enough that actually can start to smolder, it leads to very, very large fires. I call them mega fires, not in the sense that they are large in the number of kilometers, or they're large in the number of houses that they threaten, or because they threaten very quickly the people. They are mega fires, and this is something that is scientifically supported, because they consume a very large amount of fuel. They burn the soil, which has high density fuel, and slowly and difficult to suppress, and then start doing massive number of tons of biomass that go into the atmosphere with this fire. This is one of the worst cases that we have studied as scientists, is the 1997 Borneo fires in Indonesia. They lasted for about 2 months. It was a very dry summer. There were very large draining projects in Indonesia at that time, and it just led to literally thousands of smoldering fires, some of them burning at the beginning, some of them burning at the middle, some of them burning in the end. The cloud of haze that it was produced could actually be seen in the satellite, and it could be seen perfectly to be starting in Borneo. But actually it became in the news, and that's why scientists went to study it, when the cloud reached Australia and China, and it led to the first international complaint, diplomatic complaint, about emissions from one country reaching another country. And there's very little that you can do when that happens. And since then, there have been tremendous amount of progress in international agreements of what to do when Southeast Asia has a phenomena where one country is polluting the other. When Professor Page, very well known in this topic, went to the field and after the fire spent several years trying to estimate how much soil had burned, to estimate how much carbon was released in 1987, the number that she obtained with her team was absolutely beyond belief. Taking into account this was the very first time someone actually accounted for this. It was not the first peat fire, it was just the first one that scientists decided to study. And she published this famous paper in Nature in 2002, where she actually says, well, it is between 13 to 14% of the carbon emissions by humans and not accounted for. Now, since 2002, we know that the actual emissions were much closer to 13 than to 40, but it doesn't matter. 13% of the carbon emissions of humanity is more than all the cars in the world, or more than the whole of the European Union. Just this, it was not one fire, but this fire season in Indonesia in 1987. And since then, we know that every 3 years, Indonesia and Malaysia have a big wildfire phenomena. This is not only a case of the faraway, beautiful lands of tropical Indonesia. This also happens much closer to home. Pretty much every country has a smoldering fire. The question is which scientists went to study it and how well it is shared scientific case. This is a fire that happened in North Carolina. It remains the largest fire that North Carolina had ever encountered in 2008. It's called the Evans Road. It was a peatland that was very dry. It actually had a flaming fire. The flaming fire lasted for about 3 days. It was not a big deal, but what happens is that afterwards the peat left burning behind the flames. So it was a transition from flaming to smoldering, was burning for months. They could not actually stop it. Being this in North America, they actually diverted rivers, and the thousands of firefighters were extinguishing it. You can see over here the immense horizon of the fire, and you will not see a flame. The immense, all these kilometers square were smoldering without one single flame, and they were smoldering for day and night for many weeks. In this video, you can see from a helicopter, you can actually see some of the firefighters are installing over there. You can see them here. They're actually installing pumps to take the water, actually reflood some of the land in order to stop dispersation. This is the plume that you could see in North Carolina. This is a plume that is not really larger than, for example, the plume that we saw in California this year, or you will see in Greece maybe a few years ago. We saw it's not larger, but this plume was not here for 5 days, or 10 days. This plume was here for several months. So the amount of biomass that it was injected from the soil into the atmosphere was orders of magnitude larger than the fires that we are used to with flames. This is, for example, a visual image of this tree is telling you where these roots, hanging roots, is telling you where the soil was before the fire, and this is telling you now where the soil is after the fire. Obviously, this tree and hundreds of trees around, they all die, not because of the fire itself, but because of the fact that they lost their support structure in the soil. And this yellowish here that you see, orangey here, is just the ash that has accumulated, very thick layer of ash that accumulates from the mineral matter that it doesn't burn. More recently, I would say in the last 5 to 10 to 5 years, we actually have been observing with satellites the phenomena of smoldering happen also in the Arctic. These are Arctic wildfires. They do have a smoldering and a flaming component, but actually the smoldering is probably the one that is becoming very damaging to the ecosystem. And we know very little about these Arctic wildfires. And we observe them far away from the satellite. So imagine for a fire, a smoldering fire that can be seen from the satellite. If we were to get closer to it, what would be its size? This is an image of Greenland, but we know these fires also happen in Alaska, in Canada, and in Siberia. One thing that we know when we put everything together is that that smoldering has this ability. It's very easy to ignite. We can see this in the lab. We do calculations. We see this in the field. If you have a fuel, and this fuel could smolder or flame, the two of them, like happens with wood, it's much easier to initiate the process of smoldering than it is to initiate the process of flaming. It needs less heat to begin with. And actually, biomass actually has the ability of ignite at ambient temperature, the process that is called self-heating, which flamings cannot happen, whereas smoldering will become a shortcut for flaming. So it's easier to ignite. It's also more difficult to suppress. Smoldering fires actually need more water per kilogram of fuel that is burning. We can see that, we've seen that in the lab. It actually, if you were to reduce the oxygen concentration, which you don't do in fighting wildfires, but if you do that in the lab, or you're actually trying to stop a smoldering fire in a library, for example, with very important documents, one technique that we use often is to lower the oxygen concentration in that compartment. And this, you need to lower the oxygen concentration much more if it's smoldering that if you were to be doing flaming. That is indicative of how resilient, how difficult it is to suppress it. And if you were to be smothering, as we can actually do, for example, when there is a hole that is smoldering and you try to cover it, or for example, there is something burning and you dump sand on it, or you close it so oxygen cannot reach it, like for example, snow falling on a fire, you will need to hold it for months, holding time, before the smoldering will come back. Whereas with flaming, you just need to hold it for minutes and the flame will disappear. So this is telling you that, if it's the easiest to ignite and the most difficult to suppress, is because smoldering is the most persistent type of combustion on planet Earth. You will have to go to a different planet to combine the laws of nature such that smoldering is not so persistent. So there is something about smoldering on the planet Earth in terms of fire. You should not be surprised then that smoldering is the oldest continuously burning type of fire. And there is one actually in Australia. I'm going to show it to you now. This is the Burning Mountain near Sydney in East Australia. It's a nature reserve, and is the oldest continuously burning fire known to humanity, more at least 6,000 years. Some geologists say that it's probably actually more like a million years. It's not burning peat, it's just a coal seam, a natural coal seam that got ignited. It's a national nature reserve. It's also a sacred site for Aboriginals. And the interesting thing is that the fire, if you go now, this is me on top of the fire was at the bottom, very safe, don't worry. Some years it's very strong, some other years it's not, depending on the distance between the coal seam and the free surface. But you can see how the soil has been cooked. There is no trees, there is no vegetation. You can see the yellowish of the sulfur, there is reddish of the iron oxidation, there is black of the char, there is white of the ash. It's been completely cooked, and you can see meters and meters and meters of land like this. The interesting thing is that with 1800s, when the Europeans started to arrive to Australia, they actually thought that it was a volcano. So it was a particular year, 1828, you can see it over here. It was a year when the smoldering fire was particularly close to the surface, and actually it was glowing at night. It was a big plume of smoke, and they thought it was a volcano, but it was not a volcano, and it has not been extinguished and continues burning every day. If we try to understand what is it that makes smoldering ignite and what are the conditions or the type of soils that will not ignite, we have this important work. It was initiated by Franzen in Canada in 1997. We adore Franzen. He's definitely the founding father, one of the founding fathers of smoldering combustion. If you plot over here the moisture content in dry bases, from absolutely nothing of water to 2 times more water than actually there is other type of organic or mineral content. And over here you put the organic content. Here is very, very organic. All of it is organic. The solid is organic, and here you have absolutely nothing organic. These dots and this French over here is telling you that in this land over here, in this region over here, where it's very inorganic or very wet, the soil will not ignite. And then it will transition to a region over here where if it's either very little inorganic or actually it is dry, it will ignite. And this is a very useful map where you can actually already go and take samples in the field, and you can put your samples in this region or in this region or in the border between them. This is work that has been confirmed experimentally by Franzen and later on numerically by Hazelab, my group. And we consider this type of behavior a very important fundamental knowledge of smoldering combustion. This is after it ignites. I want to show you a little bit more of the imaging that you can do from the top. This is, you're seeing from the top, you're seeing the infrared. This is a layer of peat from the top. And here is a section that is dry, and here's a section that is wet. You can see how the dry is faster than the wet. It's just to show you the principle of the importance of moisture. Not only that if it's very wet, it will never ignite. Is even if it ignites, depending on the amount of water, it will go faster or slower. This is horizontal spread. And this over here is a checkerboard. We ignite at the bottom. These are wet, dry, and wet, and we have fun with this type of profiles, capture the heterogeneity that you can have in the field of wet and dry. Well, first we do the checkerboard. So you can see how the dry was the first one to burn, but then the wet stopped it, and you can see now it will propagate faster laterally because these are where the dry patches are. And now we will find the wet and it will stop again. And now this dry one over here will go faster. So at the end, this is the combination of dry, wet, dry is the fastest one, whereas these combinations had wet, dry, wet. So it was wetter than the one in the center. And we can see over here, this one, we ignite here in the center, and you can see that the ignition is very strong, but actually very quickly the drier one is able to go faster than the wet. Just to, with evidence, show you that dry peat and dry and wet peat have different behaviors. If we were to take a closer look at what happens when a slab of peat is burning, a layer of peat, we have ignited over here, and here is the peat. So for example, we start far away from the ignition. You can see this is the peat is completely unaware. This piece of peat that our fire is arriving. As you move closer to the smoldering front, then you start to find the peat that is being preheated. Its temperature is increasing because the heat that is coming from the fire by convection and conduction, and a little bit of by radiation. Then actually there's a point where it has dry enough it has preheated enough that it starts to dry, it loses its water, and very shortly after you see the charring front where the pyrolysis is taking place, and that is leaving the char, and then the char burns, and then it's actually that releases the heat that continues the preheating and the drying and the pyrolysis. So at the end, this is a process where the oxidation releases an amount of heat. A fraction of this heat is lost in the air. A fraction might be lost to the bottom and to the sides. But the important thing is the fraction that actually is able to reach the layers ahead of peat, preheat them, dry them, paralyze them, and then reuse that char that is left to continue the process. That's when you see smoldering from the top, but you can actually see smoldering from the side as well. Imagine that we're igniting here and we are seeing the depth. Smoldering has the ability to propagate laterally and also in depth, and the two different spread directions are very different. For example, laterally, which is the one that I showed you before, accelerates when the peat is dry. The downward spread, the in-depth spread, actually accelerates with water. The reason for this is actually that it finds more fuel because of the presence of water. This is something that we discovered experimentally a few years ago in Hazelab, and we continue investigating. That is fascinating that actually smoldering propagates faster inwards when it finds wetter peat until it finds so much that actually cannot propagate, but it actually accelerates a little bit with moisture. So the in-depth component is the one that will lead to what we call depth of burn. You saw the image before of a North Carolina tree where actually the soil has decreased about a meter. That's what we call the depth of burn when the fire has finished. How much is the depth where the fire has gone? And that is controlled by the in-depth spread. When we went to the field, well, not only us, but when we go into the literature and we identify the people who are going to the field to measure the depth of burn, we see that it typically goes from 5 centimeters to down to 3 meters. This is what has been ever reported in the literature. The typical average of the depth of burn for tropical peatlands, for example, is about 0.5 meter. We have a study here. We saw 2 studies of tropical region with measurements, 7 of them with boreal regions, and we see the depth of burn of tropical forest, of boreal forest, sorry, is about 20 centimeters, whereas the depth of burn for tropical forest is about 0.4 meters. You can see already typically tropical peatlands, because they are drier, they actually have ability to burn for longer, which is truly what drives the ability of these fires to produce a depth of burn. Whereas in boreal regions, they are not as dry, and maybe the cold temperatures and the rainy season arrives faster, and then they don't have as much time to propagate. And now we are finishing with the smoldering, but of course we have to mention what is the relationship between smoldering and flaming. And that actually, the relationship gives way to 2 transitions. One is a transition from smoldering to flaming. And this photo over here from California is a perfect example. You can see those embers. The great majority of these embers are burning with the smoldering. They are actually smoldering embers. And when they land on the fuel, they are actually smoldering, and they might start smoldering. Some of them, taking into account these are thousands and thousands of embers, some of them might actually transition to flaming. You can see over here what is happening in this photo, perfectly captured. This ember storm of the smoldering might lead to places, hotspots, where a flame will appear. That is a transition from smoldering to flaming. There is another transition from smoldering to flaming, where, for example, we might be having a smoldering fire that propagates for weeks and weeks and weeks. Sometimes actually it can propagate under the soil, not just burning on the surface, and actually go deeper. This, for example, could happen when there is a suppression on the free surface, and then the smoldering is able to go under, and then it transitions suddenly a few meters away into flames. And that is a transition from smoldering to flaming that firefighters are most worried about, because they might be leaving a former fire thinking that it's all clean and that it's all safe, and they might be called again weeks after saying you have to come back, the fire has returned. And it's not that the fire returned, it's that the fire never left. And this has led to the name, which is actually very exotic, and it works quite well for people. They call them zombie fires, in the sense that it's zombie because they thought it was dead, or maybe it's dead, but it's coming back apparently to life. like a zombie does. And it's so difficult to suppress, like zombies are very difficult to get rid of. The other transition, which happens very often as well, but it's actually not talked about often, is the one where flaming leads to smoldering. This, once upon a time, was referred to, still is called residual combustion, residual fires. So you have these big flaming fires, and behind they leave a smoldering, a little bit of smoldering, or a lot of smoldering, a smoldering of the trees, of the trunks, or maybe the smoldering of the soil itself. But it leads to a smoldering. This in the 90s was a significant topic of research. Interesting enough is that they rarely name smoldering by its name, by the scientific name, smoldering. They gave it all sorts of other names, and actually that led to fragmentation of the literature. It actually required for us to go back to the literature and start collecting all these studies that actually in reality has seen a little bit of the role of the smoldering, but they could not actually talk to each other because they were speaking different languages. Interesting enough is that this transition from flaming to smoldering led actually to, and this is known, to the largest emissions, even from wildfire. So you say, oh, it was a wildfire with massive amount of emissions. When they look into this, they saw that actually 1/3 was coming from the flames and 2/3 were coming from the smoldering, although they were not using the name smoldering, and this was actually classified as a flaming fire. Even then, the shadow of the smoldering was quite strong. And relating to emissions, it is important to look into the emissions of the smoldering. They led to these absolutely horrific emergencies that happens all around the world, in regions of the world that actually have a tendency to large smoldering fires, like Southeast Asia or Siberia, but actually even sometimes United States, and usually some time ago was actually in Europe. This is, for example, what happens in beautiful Singapore. This is the Marina Bay, and this is what happens in Marina Bay where there is haze. It's not that it's at night or early in the morning. This is exactly the same time of the day. It's just that the haze that has been produced by the nearby peat fires burning for weeks, the haze cloud has moved into the city of Singapore and actually has happened to be there for weeks as well. Creates massive emergency situations, respiratory emergencies in large parts of the population, especially elderly and kids or people with asthma, and actually sometimes goes to cardiorespiratory emergencies as well. This is, for example, the measurements of particle matter 2.5 microns. This is the particles that, one of the particle components that produce haze that doctors worry the most, because 2.5 microns means that actually they can go inside our lungs, to the deep ends of our lungs and into our blood system, and they start to circulate around our body. So definitely the type of components in the smoke that you don't want at all. And this line over here is the typical concentration of particle 2.5 in Singapore. Mostly this will be because of cars. You can see this, it might be healthier or unhealthy regarding to no emissions, but it's actually at the bottom, whereas here 20 times higher is what are the measurements of particle emissions 2.5 in the same location in Singapore when there is haze. It is unbearable to breathe this air. And you cannot escape of them. It's not that I get away from the road. Oh no, I'll go into the park. The haze means that the atmosphere of the region, it is well mixed smoke, and that's what anyone, people, animals, and even engines get to breathe as the component of oxygen. But it's not just Southeast Asia. It's just one of the examples. This also happens in Siberia and St. Petersburg, has happened in Moscow, has happened in Alaska, has happened in many cities around the world. And this happens. When we look into what is the composition of this smoke, it's a very complex composition, as I mentioned to you before, because smoldering is actually incomplete combustion. It obviously has a lot of carbon dioxide because actually it's meant to be product of combustion. It has a significant amount of carbon. It has a lot of carbon dioxide, sorry. It has a lot of carbon monoxide as well, which actually is poisonous. It has a significant amount of particle matter. That's the one that we worry the most. It's the thermos abundant component in peat. It has a lot of methane, which actually is a non-bound hydrocarbon. It has a lot of ammonia, and then it has this very long list of other complex molecules without an end, down to even NO is present, carbon monoxide. And the difference between the composition of a smoldering and flaming is very, very different, to the point that actually you can smell the difference. If you're trained to, we've done so many experiments with smoldering and flaming, we can actually smell the condition of combustion. For example, just looking into the ratio of CO to CO2, you have very different signatures from a smoldering flaming pit and a smoldering pit. And if we were to look into what is the particle made of, these particles that we are so concerned, this particle matter 2.5, when we look into what is it that they're made of, we look into, for example, the literature, we see that 2.5, there is a slightly higher amount of particle 2.5 in tropical fires than in boreal fires. And we see that mostly what they are made of is the red component, which is organic carbon, a little bit more of elemental carbon, and then it has the other complex molecules like pH, aromatics, PHH. At the end, we can actually draw this sketch of what would be a particle from smoldering pit, where you have a core, a complex core of actually carbon molecules that have been plugged together, and then other components, more complex, have been absorbed or condensed, and even some metals might be present there. It's a very complex molecule, very small, that actually can go deep into our bodies. And with this, I'm just finishing. If this were not to be enough to make us concerned about smoldering, there is a positive feedback mechanism between smoldering and the climate that actually has not been studied. For example, the IPCC has not considered yet this mechanism. Actually, modelers have not considered this mechanism yet. We look for what they do. And the reason is that carbon emissions, anthropogenic or otherwise, lead to climate change. Climate change in many regions of the world lead to drier soils and warmer soils. And these are red arrows. These are fire-related topics that I can discuss with you. If it's true that we have soil that are drier and warmer, that means that this organic soils that are like that are going to lead to more ignition, not just ignition because it's easier for them to ignite, but also we will have more of self-ignition, which will lead to more smoldering fires. Because smoldering fires is burning peat, mostly, not only, but mostly the smoldering fires, which is very old carbon that was stored by nature. It will take way too long, in the order of 1,000 years or more, to grow again, to capture again that carbon, which means that every single time they burn in that specific moment, instantaneously, that it burns, it becomes a net carbon emission, because we cannot grow back peatlands. Forests, we can grow them. Smoldering fires will have transition to flaming. Flaming will have transition to smoldering. But when a flame is burning biomass. It's mostly burning young trees and biomass that can grow relatively fast. And it is possible that if we grow again that forest, actually we disturb this mechanism and it doesn't become a net emission if we grow the forest within what it is, 5 years, 10 years. Which then the smoldering one creates a feedback mechanism where more smoldering fires will produce more carbon emissions, which will lead to more smoldering fires. Okay, so just concluding, just to remind you that we have discussed that there are these threats from smoldering because it's been the most persistent type of combustion, that its chemistry is at least 2 steps. In reality, it's more than 2 steps, but its minimum chemistry is 2 steps, whereas in flaming, its chemical steps could be simpler. There is char and oxidation, don't forget. Sorry, there is pyrolysis and char oxidation. That is a leading cause of fire dearth and actually and as well a damage to the earth. The footprint, the carbon footprint of smoldering peat fires is equivalent to the footprint of all the vehicles in the world, but they don't have as much press. They don't appear in the newspaper as often. It is a topic that is emerging. It's emerging not because the problem is emerging, but because science has discovered that we know too little about an important topic. That's why the science is emerging, and it's a very exciting field, which I highly recommend that you consider it. And regrettably, when we try to move the field of smoldering forward, the first thing that we found, and I'm thinking that we can use the past because maybe it doesn't happen as often. When I arrived to this topic, it was completely fragmented. The literature had so many names to refer to smoldering, and none of them were smoldering, that it was very difficult to even have a conversation one-to-one, verbally, not to speak about different papers having different concepts. It helps a lot that now smoldering, although there are different nicknames to the phenomena, scientific nicknames. At least everybody now is up to confirm that these are smoldering combustion processes, and then they might have a zombie fire, or there might be different types of applications to the type of nickname that is used to the fire. And with this, I finish. Obviously, I cannot thank enough my group for leading forward and giving me all the energy and all the support that I need to do this. And now, in the next few minutes, I'm happy to answer your questions. Thank you very much.